Welcome back. Now I am starting a new topic under electrostatics. Electrostatics is a big chapter. Under that big chapter, there is one topic called Gauss theorem. I will be starting with the part 1 of this theorem in this lecture. But before we jump to what the Gauss theorem is, why it is needed, there are a few basic things which we need to know. For example, first of all, what is an area vector? Area vector. Area vector is a vector which is attached to a given surface. Its magnitude is proportional to the area and its direction is perpendicular to the surface. For example, let's say there is a small area over here. Its area vector would be pointing in this direction. Let's say I call that dA. Let's say I point it out that this is dA. And whether it should be upward or downward, I think from vector algebra you know that. The right hand thumb rule, you know whether you are finding out A cross B or whether you are finding out B cross A. Correspondingly, you can define what would be the area vector, in which direction the area vector should point out. But what about if a surface is curved like this? Consider of an inverted bulb. It has got, or for that matter, take for example this book. What about its area vectors? If I consider this surface, the area vector is upwards, but if I consider this thing, the area vector is downwards. For this surface, area vector points outwards towards the camera. For this surface, the area vector points towards me. For this surface, area vector points in this direction, and for this surface, the area vector points in this direction. So for different parts of that surface which is not planar in nature, its different portions can be divided into small sections, and each section will have its own area vector perpendicular to that particular section of the surface. For example, let's say consider this as a ball. Now this part has got area vector A1 in this direction, this will have in this direction, this will have in this direction, and so on. So area vector is a vector which has got a magnitude which is proportional to the surface area and its direction is perpendicular to the surface. It's as simple as that. What is a solid angle? Second topic. Can you tell me what is a solid angle? We already know what is an angle. Can you tell me what is solid angle? But before I go to the topic of solid angle, first of all, I'll see again what is angle. Can you define angle? You have been using the word angle for quite a long time. You say, okay, this angle is 30 degrees, 50 degrees, whatever. How would you define angle? Actually, you can think of a problem like this. Consider a circle and I take a small section of it. Think of a pizza which is normally circular and you take a small section of it. Now that section is representing the part of the circle. Now how big that part is, that is what you call as an angle. For example, if I take out of pizza, I've got a pizza and I divide it among 4 people, then one section is 1/4 of the circle and you say it subtends an angle of pi by 2 because the total angle has been assumed to be 2 pi. Has been assumed to be really assumed, or can you prove that the total angle is 2 pi? I think we can. First of all, we will have to define angle. If this is the length of the arc and this is the radius vector, then you define this angle in terms of radians as L over R. Theta is L over R radians. Now, if I have got a full circle, what is the total angle subtended by a full circle at its center? The total length of this arc is equal to the circumference 2 pi r divided by r, and we know that the angle subtended by a full circle at its center is 2 pi, and since it has been divided into 4 sections, one section is subtending 1/4 of the total angle, that is 2 pi by 4, which is equal to pi by 2. So this is how you can define angle. Angle is not a unit. In lower classes, while dealing with units and dimensions, you are studying that these are called supplementary units. These are not units, because unit is always of the same size. It is not representing physically same size. For example, if I've got a smaller pizza and I've got a bigger pizza, I divide it into 4 sections. This section has got pi by 2 radian angle. This section also subtends pi by 2. Can we say that this section is equal to this section? The answer is no. They are physically different. They are representing, the angle is representing how much part of the circle. Circle का चौथा हिस्सा. अब सर्कल छोटा है तो छोटा हिस्सा, उसका चौथा हिस्सा भी छोटा होगा. सर्कल बड़ा है तो उसका चौथा हिस्सा भी बड़ा होगा. This is not a unit. This is representing section of a circle. How much part of the circle is being represented, that is what you call as planar angle. Now extend your discussion in the same way from the part of a circle to being part of a sphere. Think of a football now. From pizza, shift to a football. Think to a football. You all have seen a football. You have got hexagonal sections like that on a football. The black and white hexagonal sections, I hope you can imagine. Imagine that you join one such hexagonal section to its center. What you would get? You would get a kind of cone. And how the sphere has been made? Can you visualize it? Try to visualize it try this visualization of sphere as if sphere is made up of large number of cones which have been put together to fit their corners, their apex cones at the center at one point, and that will make a sphere. Now, if you take a bigger patch on the surface, you will have a bigger cone, and if you take a smaller portion of the surface, you will have a smaller cone. So the solid angle is something, as in case of planar angle, the angle represents part of the circle. How much part of the circle that section is representing, that's what you call as planar angle. And similarly, here how much part of the sphere is being represented by that cone, that's what you call as solid angle. Solid angle is generally denoted by d omega, and d omega is given as, for example, the theta was called L over r, the length of the arc over radius vector, which was dimensionless by the way, and units were radian. Now d omega is this section dA, surface area dA divided by radius square, or ds, whatever you want to call it, ds by a square. That is what you call as solid angle, ds. And you measure it in steradians. You measure it in steradians. So, what is the total solid angle subtended by complete sphere at the center? Just imagine how we did that. We tried to find out total length of that arc, which comprises the complete circle. That was 2 pi r divided by radius. Now what about the sphere? The total surface area divided by the radius square. The total surface area of a sphere is 4 pi a square divided by a square. So what is the total solid angle subtended by a sphere at the center? Total solid angle subtended by a sphere at the center is 4 pi steradians. Total solid angle subtended by a sphere at the center is 4 pi steradians. Is that okay? Or should I generalize it? Solid angle subtended by any closed surface at any point inside it is always 4 pi steradians. Can you prove that? Pause the video, think about it, and come back. Let's prove that total solid angle produced by any closed surface at a point inside it is always 4 pi steradians. See how can we do that? I again start from the planar. You know, this is a circle, and let's assume that this angle is, just for the sake of an example, 30 degrees. What if I extend it? What would be this angle? You already know it would always remain 30 degrees. No matter how far away I go, I'll always get 30 degrees as long as the lines go on extending themselves in the same direction. It will still be 30 degrees. Let's assume, okay, now you have got different sections. Section number 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. That's for the second example. Now what is the sum of total angles which these sections are subtending at the center? You know, it is 2 pi radians or 360 degrees. Think of any irregular closed shape, which is not circular obviously. But what you can do, you can imagine, and now you wish to find out what is the total angle subtended by this closed line, closed curve at any point. Let's say at this point. At this point, what is the total angle subtended by this closed surface? Can you prove it is 2 pi radians? Imagine a circle over here, and imagine those 10 sections like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, and let's say 10. Now, sum of these 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Oh, by chance it turned out to be 11, no problems. Now, the total sum of these sections, sum of total angles subtended by these sections at that point is equal to what? You can see the circle, it's 2 pi. And if this is, whatever this angle is same. Whatever this angle is same. So sum of all these angles would always be again same as the angle subtended by this circle. I hope you are there. If this angle is 30 degree, this angle would be 30 degree. If this is 30 degree, this would be 30 degree. If this is 10 degrees, this would be 10 degrees. And so on. The sum of all these angles, 1, 2, 3, 4, 5, and whatever, that would again be equal to 2 pi. Now, again, generalize this thing to any arbitrarily shaped closed surface. What is the total solid angle subtended by that arbitrarily shaped surface at a point inside it? I know how. You know how to do it now. We know what is the total solid angle subtended by a sphere at the center. This is 4 pi, and you can extend it. And if there is any closed surface of arbitrary shape, the total solid angle subtended at this point, because this angle would be same as this angle. Therefore, the sum of individual solid angles subtended by the sphere is same as the total solid angle subtended by this arbitrary shaped closed surface. that is equal to 4 pi steradians. This is an important information which will be quite often used. I think this is enough for this part. In next part, I'll